All right, so today we are going to prove the spectral theorem. So this is a very important result which tells us how to decompose normal or self-adjoint operators, depending on the field of scalars, into orthogonal projections, which makes it easier to analyze them by reducing them to these simpler pieces. Okay, so let's begin with formulating the result. So this is theorem 625. Okay, so the situation is as usual. So suppose T is a linear operator on V, where V is an inner product space, okay, over some field of scalars F. So as usual, F is either the real, the field of real numbers or the field of complex numbers. And we assume that the inner product space is finite dimensional. So the dimension of V is less than infinity. Okay. Now let lambda 1 through lambda k be scalars in F. So let this be the distinct eigenvalues of T. Okay. So this lists all of the eigenvalues of T. And we assume that T is normal if the field of scalars is C, or T is self-adjoint if the field of scalars is the reals. So if F is equal to R. Okay, so this is the usual distinction of two cases where we always have to assume a bit more when working over the field of reals, because not all polynomials split, right? So remember, for various results, we always have to assume self-adjointness, the stronger condition, when we are over the reals, and normality is sufficient over the complex numbers, as usual, okay? So these are the assumptions. Now, for each I between 1 and k, we'll let Wi be the subspace corresponding to E lambda I. So this is the eigenspace eigenspace of T, right? Corresponding to the eigenvalue lambda I. So corresponding to lambda I, okay? So for each eigenvalue, we'll let Wi denote the corresponding eigenspace. Okay, so now if we have a subspace, we can consider the orthogonal projection onto it. So we let Ti be, this is Ti, not T1. Let me write it clearly. So let Ti be the orthogonal projection of V on Wi, okay? So it's a linear operator of very special kind. The orthogonal projection on the ith eigenvalue, eigenspace of T, sorry, okay? All right, so this is the setup. So then we have the following properties. Okay, so A, we have that V is given by the direct sum of these eigenspaces. So V is equal to W1, direct sum with W2, etc., direct sum with WK. Okay. B, we have, if we denote by Wi prime, if we let this be the direct sum of Wj for all j not equal to I, okay? So fix I, we'll look at the direct sum of all the remaining ones, Wj's. Then we have that the orthogonal complement of Wi is precisely Wi prime. Okay, so we have that these the subspaces in this direct sum, they're all orthogonal. Okay, condition C. We have that Ti composition with Tj is equal to delta Ij times Ti. And this holds for all Ij between 1 and k. Okay, so we recall, as usual, delta Ij is the Kronecker symbol, so it's just equal to 1 if I is equal to j, and 0 if I is not equal to j. Okay, so you see that these compositions as of two Ti and Tj, this composition is simply equal to Ti. So it means Ti square is equal to Ti, right? But it's zero, the zero linear transformation, if I is not equal to j. Okay. We also have D, I, the identity linear operator on V, is given by the sum of the t's. So it's T1 plus T2, etc., plus Tk. Okay. Sometimes one says in this case that the identity is resolved by the sum of these linear operators, or that this is the resolution of the identity operator. Okay, and finally, E, the linear operator T itself is given by the following linear combination. So we have lambda 1 times T1 plus etc. plus lambda k Tk. Okay, and this expression is referred to as the spectral decomposition of T. Okay, so we have written the linear operator T that we're starting with as a linear combination of orthogonal projections on the eigenspaces of this operator. Okay, and the coefficient in front of the projection onto the ith eigenspace is the corresponding eigenvalue. Okay, finally, when we have a situation like this, then the set consisting of lambda 1, lambda 2, etc., lambda k, so the set of all distinct eigenvalues of T is called the spectrum of T. Okay, the spectrum of the operator. All right, so this is the theorem. So it tells us how to decompose a normal in the case of complex numbers, or self-adjoint in the case of real numbers operator, into a linear combination of projections, orthogonal projections on its subspaces. It's only called spectrum if all of the above hold. No, sorry. It's always called. So the spectrum of a linear operator is simply the collection of its distinct eigenvalues. Okay. Okay. All right. Yeah. So this is the theorem. So the idea, yeah, as you see, we're trying to decompose T, which is a general normal or self-adjoint operator, into a linear combination of more explicit operators, simply just the orthogonal projections onto some subspaces. Okay, so let's prove this. So this will be a combination, the proof will consist of the combination of various results that we have obtained over a series of the previous lectures. So I'm going to start the proof on the next page, okay? But I can return if you need to look it up, just let me know. Okay, so first we're going to prove A. So let's go back for a second. So A says that V can be written as a direct sum of the Wi's, where Wi's are the eigenspaces corresponding to the distinct eigenvalues, okay? So this part is easy from what we know. Because by theorem 616, if f is the complex numbers, and by theorem 617, if the scalars are the real numbers, we know that T is diagonalizable. Okay. So because we're assuming that it's normal, either normal or self-adjoint, so we know that then it's in particular diagonalizable, right? It's a stronger condition. Okay, but if we have a diagonalizable operator, then we know that we can be written as a direct sum of its eigenspaces, right? So hence V is the direct sum of the W's, the eigenspaces. And this is by theorem 511, which tells us that for a diagonalizable operator, the whole space is the direct sum of the eigenspaces of this operator. All right, so this is just part A. Next, let's show B. So let me go back to the statement again for a second. So B tells us that the orthogonal complement of Wi is given by the direct sum of all the other W's. Okay, so to show this, we just have to pick a vector. So let's take X in Wi. Okay, so fix I, first of all, fix I, and let X be a vector in Wi and Y a vector in Wj for some I not equal to J. Okay, so what's the inner product of these two vectors? So we have that the inner product of X, Y is equal to 0. This is by theorem 615D. Okay, so we know that the inner product in this case is going to be 0. Hence, we have at least one inclusion. So we have that Wi prime is contained in the orthogonal complement of Wi, right? Because we took X to be an arbitrary element of Xwi, and we took Y to be from any of the Wj's for J not equal to I. And we have shown that then X and Y are orthogonal. Okay, so X, since X was any vector here, we have demonstrated that each Wj is contained in the orthogonal complement of Wi. And so the direct sum is also contained, well, or just their sum is contained in the orthogonal complement of Wi as well, right? So this gives us this inclusion, but we also have to show that it's actually equal. Okay, so we have to show the opposite inclusion. Oops. So for that, by part A, we have the following for the dimensions of the spaces. So we can write that the dimension of Wi prime is going to be equal to the sum of the dimensions of Wj over all J not equal to I, right? Because this we're looking at direct sum of these subspaces. I mean, Wi prime is defined to the direct sum of these subspaces. Okay, but the dimension of this is just the dimension of V minus the dimension of Wi, right? Because we took because the whole space is the direct sum of all W's, and so if we take the sum of the dimensions of all but one, all but the ith one, the dimension then is given by this, right? Okay, so we have this estimate for the dimension, and on the other hand, we have that the dimension of the orthogonal complement of I is equal to the dimension of V minus the dimension of Wi. Okay, so this we know, this was theorem 67C. Okay, So when we have a space and we have a subspace and its orthogonal complement, then the dimension is given by this expression. Okay. Hence, the conclusion by comparing these two expressions is that the dimension of Wi prime is equal to the dimension of Wi perp, the orthogonal complement, right? So again, this comes from comparing these two lines, right? Because here we have the dimension of Wi prime expressed in terms of the dimension of phi and the dimension of Wi, and here we have the same for the dimension of Wi perp. Yeah, these are two expressions are the same. So then they are equal. And so look, so we have that Wi prime with a subspace of Wi perp, but the dimension is the same. So combining these two, it follows that in fact Wi prime is equal to Wi perp, right? Because if you have a subspace of the same dimension, then it actually has to be equal. Okay, so this tells us, gives us part B. Now part C, which says that we have these claims for the compositions. So this is going to be part of the homework. Yeah, but you should see that it looks familiar, right? Because we know that if remember Ti is an orthogonal projection, right? So we know that for projections, the square. So like if T is a projection, then T square is equal to T. This we already know, right? So this would give the value for Ti composition with Ti. So for the case when I is equal to J, and you have to argue that in the other cases, because these subspaces are orthogonal, you can get that the composition is going to be the zero linear operator when I is not equal to J. Okay. So this is part C. So next, let's show part D. That the sum of all these linear operators together is just the identity linear operator. Okay, so part D. So what we know? So we know again that Ti is the orthogonal projection of V on Wi. Okay. From part B, we have that the null space of Ti is equal to the orthogonal complement of the range of Ti, right? So remember, this is the property of a defining property of orthogonal projections. But this is equal to Wi perp because again, Ti is a projection on Wi, so the range of Ti is Wi, right? That's why we can replace it by Wi here. And this we have just shown in B, it's the same as Wi prime, the sum of all the other eigenspaces. Okay, so this gives us an expression for the null space. Now by part A, every vector x in V can be written as a sum of vectors from the corresponding subspaces, right? So we can write x is equal to x1 plus x2, etc., plus xk for some, in fact, unique choice of the vectors xi in Wi, right? Because the whole space is the direct sum of the Wi's. Okay, but then we have that if we try to evaluate Ti on x, okay, so what do we get? We have to, we can replace x by the sum, so this is Ti of x plus x1, sorry, x2, etc., through xk. Now Ti is linear, of course, so this can be written as the sum Ti of x1 plus etc. plus, and now we pay attention to what happens in the ith position. So we have ti of xi plus ti of xi plus 1, etc., plus ti of xk, right? So we have this, and because this is an orthogonal projection, well, it's a projection on wi, so we get that in fact this is equal simply to ti of xi, right? By definition of projections. Because all these other coordinates, all coordinates except for the xi of the vector x, they all belong to the orthogonal complement, right? So hence the result of applying ti should be only the component in the sum which belongs to wi. So just apply to that, okay? So we get this definition of projection. So I'm also using that xi is in wi, okay? So we have this since the sum xj I not equal to j belongs to wi prime. So like I said, yeah, which is the null space of ti. And so we get that t applied to the sum over all I not equal to j xj is equal to 0. Okay, so we have this. Okay, so what does it tell us about x in the end? So we get that x is equal to, well, let me stress here. So here we get the equality, right? We get that this is equal, so this expression, ti of xi, is actually equal to xi, right? Because we are projecting on wi. So the image is the component of the sum, which is in the subspace, right? Which is exactly xi. Okay, so we get that that was 0. And so we conclude that x can be written as t1 of x plus t2 of x, etc., plus tk of x. Okay, so we have this for all x in V. All right, but that's exactly what we wanted. So we get that the identity operator on V is equal to the sum t1 plus t2, etc., plus tk. So this shows that the sum of all these linear operators is the linear operator, which is just the identity operator, sending x to x. Yeah, okay. So this gives part D. Now we want to get the main point. So part E, namely that, let me go back to the statement, namely that T itself is the linear combination of the TIs of this form, where the coefficient in front of TI is the eigenvalue corresponding to the eigenspace Wi. Okay, so let's check it. So take any x in V. Okay, then again we have x can be written as the sum x1 through xk for some xi an element of the subspace Wi, because V is the direct sum. Then we have that applying t to x by linearity of t is the same as applying t to x1 plus etc. plus t of xk. Yeah, this is just linearity of t. But they are eigenspaces, right? So remember, Wi is the eigenspace corresponding to the eigenvalue lambda I, and xi is in it. So then t of x1 is going to be simply lambda 1 times x1, etc., lambda k times xk. right? Because, like I said, Wi is the eigenspace corresponding to lambda I. Okay, but in turn, this can be written as lambda 1 T1 of x plus etc. plus lambda k tk of x, right? Because projecting on the corresponding subspace only gives us the component of x corresponding to the subspace, these are projections, right? So we get this, but now we can combine this. So this is the same as, by definition, right? So this is the same as taking the linear operator formed by lambda 1 T1 plus etc. plus lambda k tk and applying it to x. And this part here we have by D, this equality, right? Okay. And this is what we wanted, right? Because x was an arbitrary vector in V. And we have demonstrated that T of x is equal to this linear combination applied to x. So we conclude that T is equal to lambda 1 T1 plus etc. plus lambda k tk. Because we have this for any vector x and v. Okay, so this concludes the proof of the spectral theorem. Okay, so you see, mostly it was the combination of various results that we have already developed so far. We just had to combine them in the right way. Okay, so yeah, I'll pause for a minute if there are any questions. Okay, if not, let us collect some corollaries and applications of this spectral theorem. So it is useful, as you will see, for many other results. So first of all, let me start with a remark. Okay, before developing some corollaries. So what do we have at the level of matrices in this picture? So assume that beta is the union of orthonormal bases of the subspaces Wi. Okay, and let Mi denote the dimension of the corresponding eigenspace Wi. Okay, so we know that the union of orthonormal basis for each Wi is going to be an orthonormal basis for the whole space, right? We know this. And so it means we can write a matrix representing T with respect to this choice of beta. So then this matrix is going to have special form. So it has the form which looks as follows. So it consists of a bunch of blocks where we have the only non-zero blocks on the diagonal, and the blocks look like lambda 1 times the identity matrix of dimension M1. Then we have the block corresponding to lambda 2 times the identity matrix on of dimension M2, etc. Okay, and they're square matrices. Sorry, I'm drawing them as rectangles, but they should be squares. Okay, just to save some space. So these are all square matrices, square blocks on the diagonal. M1 by M1, then M2 by M2, etc. All the way through the eigenvalues. So in the end, we have lambda k, that mk by mk identity matrix, and we have zeros outside, right? So in words, we get a diagonal matrix, right? Because look, if this, since this is the identity matrix on in each block, it's again diagonal, and we just have lambdas the corresponding, for example, lambda 1 on all positions on the diagonal for the first M1 entries. Then we have lambda 2 continuing along the diagonal. Then we have lambda k in the end. Okay, so this we get a diagonal matrix whose, oops, what did I do? Became thick for some reason. Okay, I don't know what I've done. I guess we're going to write in a slightly thicker font now. Let me see. Okay, so we get a diagonal matrix whose entries on the diagonal are exactly the eigenvalues lambda I, okay? So this is the only things we have on the diagonal, and each eigenvalue lambda I is repeated mi times as we go down the diagonal. Okay, so we get a matrix of this particularly simple form. On the top right, okay, I see, thanks. Yeah, I was actually going to ask, top right. Ah, okay, this is what I pressed. All right, thanks. Yeah, thanks a lot. Yeah, okay. All right, yeah, so we get that the matrix has this very special form with respect to such appropriate choice of the basis, right? So the basis has to be chosen as the union of the orthonormal bases for the subspaces. Okay. So now let's collect some corollaries. So we need an auxiliary lemma, lemma 1. So if we have that T is equal to lambda 1 T1 through lambda k tk, so if this is the spectral decomposition of T, so meaning that TIs are the orthogonal projections onto the on the eigenspaces of T, like in the theorem, then we can evaluate G of T, where G is an arbitrary polynomial, and this can be written as G lambda 1 times T1 plus etc. plus G of lambda k tk, and we have this for any polynomial G. Okay, and the proof of this lemma is is again going to appear on the homework, but the idea here is not very difficult. Yeah, so you need to plug T into the polynomial. So T is given by this expression, and the only difficulty is when we look at things like Ti to some power, for example, k, right? And we know what to do with those because these are projections. Okay, so you will see that this simplifies quickly using that Ti, each Ti is a projection in particular. Okay, so we have this simple way to evaluate a polynomial on a linear operator if we know the spectral decomposition for it. Okay, all right, so now we can, given this remark, we can obtain several quick corollaries of the spectral theorem. So throughout all these corollaries, we will assume, excuse me, that T is a linear operator on V. V is an inner product space over some field of scalars F of finite dimension. Okay, so this is the assumption. Then we have corollary 1. If F is in fact the field of complex numbers, so we have a complex inner product space, then the linear operator T is normal if and only if the adjoint of T, T star, can be written as G of T for some polynomial G over F. Okay, So we have this new characterization of normality of a linear operator. So normality means exactly that, well, we have if and only if that the adjoint can be represented by as some polynomial of T itself. Okay, so let's prove this equivalence. So as usual, this means we have to prove two implications. So first, we show the implication from left to right. Okay, so suppose T is normal. Okay, so what we just learned, the spectral theorem, since T is normal, we can find the spectral decomposition for it. So we can write T as lambda 1 T1 plus etc. plus lambda k Tk. So let this be the spectral decomposition of T by theorem 625 that we just proved. Okay, then if we want to calculate the adjoint of T, so we can substitute this expression for T. So we have lambda 1 T1, etc., lambda k Tk, and we are taking the adjoint of this. And now we can use the properties of the adjoint operators, right? So we know that this can be then written as lambda 1 complex conjugate T1 plus etc. plus lambda k complex conjugate Tk. Okay, so what am I using to get this? So here we are using theorem 611 to conclude that taking the adjoint is a linear operation, but you have to take complex conjugation of the coefficients. The only point is that in principle, if I apply this, I would get lambda 1 bar T1 star, right, plus etc. plus lambda k bar Tk star. So these are just the properties of the adjoints, theorem 611. So how do I get from T star to Tk? Well, remember, these are orthogonal projections. So we have that Ti is equal to Ti star by theorem 624. Okay. So we know that orthogonal projections are in particular self-adjoint. Okay. So this gives us this expression. But look, this expression is good because this is a polynomial, right? So we have, well, okay, sorry, we're not done yet. I mean, we need a bit more. We need one more step. Okay, it's not obvious that it's polynomial yet. Sorry, I'm rushing a bit. So what we need to understand is actually how to get this polynomial from this equality. And here we need to use a fact from algebra that I'm going to state without a proof, but you probably saw it in some form. So this is fact, and this is what is called Lagrange interpolation. Okay, so there's a fact which tells us that for any field f and any scalars C0 through Cn, so we have n plus 1 scalars in f. Okay, note altogether we have n plus 1 scalars. Okay, which are all pairwise distinct. So we have Ci is not equal to Cj for all I not equal to j. And any scalars B0 through Bn in F, okay? There exists a unique polynomial g of t of degree n, so this is the same n as we have here, yeah, over f such that the values that G takes on Ci are precisely Bi. So we have this for all I from 0 through n. Okay. So the idea again. So what is it telling us? So if you have a bunch of points on the plane, you can draw a curve through them, given by a polynomial equation. And the number of these points is important here. So it is telling us that we can always find a polynomial which goes through these points. So it takes the prescribed values on the prescribed points. And moreover, it is unique. Yeah. So as long as we have specified n+1 points, so remember again, it goes from 0 to n. So we have n+1 points altogether. Then this determines the polynomial uniquely with this property. All right. So this is a Lagrange interpolation. So now we're going to use it. So using this to find the polynomial which represents T star from T. Okay. So using this fact. Okay, let me. So this is a separate fact. Yeah. Using this fact, we can choose G. So now returning back to our proof. So we can choose G, a polynomial, such that we have G of lambda I is equal to the complex conjugate of lambda I, and that we have this for all I from 1 to k. Okay. And importantly here, remember lambda I is a distinct eigenvalues. Okay, so recall lambda I are distinct eigenvalues. So it means we have distinct points, which give, so we can find a polynomial like this. Okay, but then we have that G of T is equal to G of lambda 1, T1 plus etc. plus G of lambda k tk. Okay, so how do we have this? This is by the lemma. So by lemma 1. Okay, let me go back one page for a second. So lemma 1 tells us that evaluating a polynomial on T corresponds to just evaluating it on the coefficients, right? When we represent T as a spectral decomposition. So if we go back here, G of T is going to be just G of lambda I times Ti and take the sum over all I. But now by the choice of G, okay, so by the choice of G, we have prescribed values for these arguments, right? So we know that this is the same as lambda 1 bar, T1 plus etc. plus lambda k bar, Tk. Okay. But what is this? So this is exactly T star, right? Because above we have calculated this this part, that T star is equal to this expression, and so this is exactly the same expression. And so plugging it in, we get that this is exactly T star. Okay, so G of T is equal to T star. So this gives one direction of the equivalence. So it tells us that we can represent T star by some polynomial of T. So now let's show the converse implication. So assume we already know that T star is equal to G of T for some polynomial G. Okay, so some polynomial G of little t, the variable, which as usual, we can write any polynomial as a0 plus a1 t plus etc. plus an tn for some scalars, right? So for some ai in f. Okay, But then by linearity of T, we have that taking the composition of T with T star, this is going to be the same as applying T to this expression of T star. So we have T of A0 plus A1T plus etc. plus AN Tn, right? So I just plugged in the assumed expression for T star. And now we use linearity of T. So this is going to be the same as A0 T plus A1 T square plus etc. plus AN T n plus 1. Yeah. So note the power grew by 1 on each step because now we're composing with T. So it was n, now we get n plus 1 in the result. Okay. But now we can take T out of the brackets, so to say, yeah, because remember, we know that composition, by the basic properties of composition of linear operators, we have that this can be written as A0 plus A1T plus etc. plus AN Tn, right, times T, where by times, again, we mean composition. So everything here is an operator, so multiplication corresponds to composition notationally, right? Okay, but this is just T star composition T. Okay, so what we have obtained then is that the composition T star is equal to the composition T star T. So the operators commute. T commutes with its adjoint, so this means that T is normal. Okay, so this concludes the proof of the first corollary. Okay, so let me go to the next page. Okay, there are a couple more corollaries. I don't want to rush you through them, so I think we'll do the remaining corollaries next time. So I'll stop here for today. Yeah, I think it's a good place to stop. So we see that thanks to the spectral theorem, we have this nice presentation of the adjoints, right, for normal operators. So normality is the same as adjoint being given by some polynomial of T. Okay, and next time we'll see more corollaries.